Howdy, howdy. This is Mr. Potter. In our previous lessons for Chapter 8, we've been talking about what happens as x increases without bounds. Really, we've been talking about the limits as x approaches infinity, or the limits as x approaches some issue with our domain, which we might have to approach from the left or from the right. The whole reason that we've been doing this is because there are a lot of situations where in physics and in engineering and in medicine, we talk about what happens as x or t or some other independent variable goes on without bound. And we need to understand what's going on in those situations. That's the whole purpose of dealing with limits as x approaches infinity. And we saw this in our early algebra and pre-calculus classes when we were talking about asymptotes. But I want to talk about another application of this. So I'm going to come up with a very simple area function, because I know that the graph of y equals e to the negative x is a fairly well-behaved function. It's the reciprocal of the exponential function. So it's going to approach x equals, it's going to approach y equals 0 as x increases without bound. And what I'm doing is I'm going to find an area function, because I can find the area from 0 up to the point x, and I can come up with the formula for this, because I know that the area up to x is a definite integral. The integral from 0 to x of my function e to the negative t dt. And this is a function that I can find the antiderivative of analytically. I need to do u substitution. I need to let u be negative t. So du would be negative 1 dt. And all I have is dt. So this really ends up being negative du. And so this becomes the integral from t equals 0 to t equals x of negative e to the u du. And this is a pretty straightforward antiderivative. This ends up being negative e to the u, which I'm going to evaluate from t equals 0 to t equals x. And I've got a mismatch of variable here, so I really want to resubstitute my u back in. So this ends up being negative e to the negative t, evaluated from t equals 0 to t equals x, or negative e to the negative x minus negative e to the negative 0. Now, negative 0 doesn't make sense, and the e to a 0 power is 1. So this really ends up being 1 minus e to the negative x. And so this is my area function. I can say that the area under this exponential curve up to the point x can be given by this formula, 1 minus e to the negative x. And I can even substitute some value. So if I want the area up to x equals 1, this would be 1 minus e to the negative 1 power, which is approximately 0.632. If I want to find the area up to x equals 2, that's going to be 1 minus e to the negative 2, which is approximately 0.865. But if I want to find the area up to x equals 10, I get 1 minus e to the negative 10 power, but my calculator tells me this is 0.9999955. In other words, this e to the negative 10 power that I'm subtracting is negligible. And in reality, it raises the question, could I feasibly talk about the area under this curve starting at 0 and going off to infinity? In other words, could I really look at the limit as x approaches infinity of this area function? Because it really should be the limit as x increases without bound of 1 minus e to the negative x. And I know that this graph approaches 0 as x increases without bound. So this limit actually ends up being 1. So what I've got here is I've got an area that's bounded by an infinite graph on the top. It's bounded by an infinite axis on the bottom. And yet the area contained between these two infinite lines is a finite positive number. And so this brings up a really interesting idea, because I really could think of what I've written up here as a definite integral involving infinity. So this is really the integral from 0 to infinity of e to the negative t dt. Now, we've been throwing around infinities throughout chapter 8. What we really need to realize is infinity is not a number. Infinity is a concept. And when I say the limit as x approaches infinity, x is increasing without bound, or x is going to the far right of the x-axis. This isn't an actual number that I can substitute. What makes this really interesting is that I have this limit where x increases without bound, but I get a finite result from it. And so this idea of using infinity as one of our limits of integration is called an improper integral. So an improper integral is going to be finding the integral from some value a to infinity of some function dx. And the way that we approach this is we're going to be treating this as a limit, as some value which I'll call b approaches infinity. And I'm really finding the definite integral from a to b of my function dx. And usually this will be something that I can find the antiderivative of analytically, and then substitute in for b and for my lower limit a, and then try and evaluate the limit. And we've talked about how to evaluate these limits at infinity throughout chapter 8, and in fact back in chapter 2 as well. So I want to go through a couple of examples here. So I'm going to go ahead and do an example for this function. Let's say I want to find the integral from 1 to infinity of 1 over x dx. Now remember, I can't actually substitute in infinity. I actually need to treat this as a limit. So I've got the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. And this is something I can find the antiderivative of. This is the natural log of my argument, which I'm going to be evaluating from x equals 1 to x equals b. Of course, b is the variable of my limit. b is increasing without bound. So when I substitute, I get the natural log of b minus the natural log of 1. And again, b is increasing without bound. I can't get rid of b until I actually try and evaluate the limit. And in doing so, notice, of course, the natural log of 1, that's 0. But if I take a look at the natural log function, the natural log function, even though it's slower growing than any of the other polynomial functions that we talked about, this does increase without bound. And this limit does not exist. And so it's really important to note that even though I'm treating these integrals with infinity as if they were real numbers, it is entirely possible for me to get an answer that just doesn't work. In other words, not all of these improper integrals behave the way that I expect. So I want to do one more example of this. I did my first example with e to the negative x, and it behaved very, very well. But if I try and do the integral from 0 to infinity of e to the x dx, you can see that I'm going to have some problems. You know that the exponential graph increases without bound. And if I'm trying to find the area under this curve forever, I'm clearly going to get an unbounded error. I'm certainly going to be having an infinite area here. But I need to treat this as a limit problem. The limit is b approaches infinity of the integral from 0 to b of e to the x dx. So the antiderivative of an exponential is the exponential function, which I'm evaluating from x equals 0 to x equals b, as b increases without bound. So I've got the limit as b approaches infinity of e to the b minus e to the 0. And this limit does not exist. This limit is unbounded. This is really an infinity minus 1 situation. And so this integral, the integral from 0 to infinity of e to the x dx, we call it divergent. And divergent means that we're dealing with a value that is not a finite value. Maybe it's infinite. Maybe it's a limit where the values alternate between positive and negative values, which we saw back in chapter 2 as the limit as x approaches infinity of sine x. We know that sine ranges between negative 1 and positive 1. It's not going to increase without bound, but it certainly does not approach a particular value. And so whenever I can't get a single solitary value, an answer for these improper integrals, I'm going to call it divergent. And it's really easy to see what the situations are. The two examples we've talked about, e to the x and natural log x, these are all situations where as x increases, our function also increases without bound. And so it's kind of easy to see that in order to get a value that works, I'm definitely going to be needing to look at situations where my value is not increasing as x approaches, but decreasing as x increases without bound. Say like y equals 1 over x, a function like this. And so I can certainly talk about the area from 1 on as being the integral from 1 to infinity of 1 over x. But we saw that we got natural log x out of that. And so this is not going to work. Just because my function approaches 0 does not necessarily mean that the area is going to be defined. I still have to treat that limit, and I still have to evaluate that limit as x increases without bound. But there are plenty of situations where it does exist. So I want to take a look at the integral from 0 to infinity of 2 over x plus 3 times x plus 5 dx. So this is the area under this curve, and I notice that I've got a product in the denominator, so I'm definitely going to have to do the partial fractions route. So looking at this from a partial fraction standpoint, I know that 2 over the quantity x plus 3 times x plus 5 is really equal to a over x plus 3 plus b over x plus 5. And when I cross multiply, I end up with 2 equal to a times x plus 5 plus b times x plus 3. And so when I do 5 times a and 3 times b, my constant is equal to a constant plus a constant. And I have no x's over here. So this ax and bx has to add up to 0. So if a plus b equals 0, then certainly 3a and 3b add up to 0. And I can actually solve using elimination that a ends up being 1. And of course, if a equals 1 and it has to add up to equals 0, b must be negative 1. So the problem that we're actually trying to evaluate is the improper integral from 0 to infinity of 1 over x plus 3 minus 1 over x plus 5 dx. Now, this is an improper integral, so I do need to treat this infinity with care. So what I'm going to do is rewrite it as the integral from 0 to b, and I'm going to be doing the limit as b increases without bound. So I'm going to have 1 over x plus 3 minus 1 over x plus 5, integrating that dx. So this is going to be the natural log of x plus 3 minus the natural log of x plus 5, which I'm evaluating from x equals 0 to x equals b as b increases without without limit. The issue here is that in our previous example, we saw that natural log was something scary because we know that the natural log function increases without bound. But we also notice that when we subtract logarithms, we can put the argument together. So I'm really going to have x plus 3 over x plus 5. And I'm using parentheses instead of absolute value because on this domain from 0 positive, these expressions aren't negative. So I'm going to evaluate this from x equals 0 to x equals b, and then take the limit as b increases without bound. So this is going to be the natural log of b plus 3 over b plus 5 minus the natural log of 3/5. The limit as b increases without bound. So I'm looking at this, and this limit deals with a ratio of two expressions. And L'Hopital's rule seems like it was made for this. So if I look at this, where I do have an infinity plus 3 and an infinity plus 5, I do have that indeterminate form. And so the derivative of b plus 3 is 1. And the derivative of b plus 5 is 1. So I really have the natural log of 1. Well, that's nice. In other words, my area is really the negative natural log of 3/5. Now, of course, you're looking at this and going, wait a minute, this area is negative? And not really. Remember that a negative really means that this is the 3/5 raised to the negative 1 power, which is the natural log of 5/3. And because 5/3 is bigger than 1, this actually is a positive area. So it's certainly a perfectly reasonable area for this function. I'm still looking over these old techniques, and so I'm bringing back some of the techniques that we talked about back in chapter 6, how we find these antiderivatives of more complex functions as a review. But we're still looking at it now from the purveyance of I've got an integral that involves infinity. I've got a limit that involves infinity. And one of the key ways that we saw to deal with those limits of infinity, especially if I have an indeterminate form of infinity over infinity, was using L'Hopital's rule. So I want to do one more example here. So I'm going to take a look look at this example here, I'm going to give you the definite integral from radical 3 to infinity of 1 over 1 plus x squared dx. Now, the very first thing you always have to do is to get rid of this infinity. We can't deal with infinity. We have to deal with it as a limit. The limit is b approaches infinity of the integral from radical 3 to b of 1 over 1 plus x squared dx. And now I need to take a look at what is this function that I'm trying to take the antiderivative of. And it turns out that this function is a really nice function to work with. It ends up being the inverse tangent function. So I'm evaluating this inverse tangent function from x equals radical 3 to x equals b, and then taking a look at the limit as b approaches infinity. So what I've got here is I've got tan inverse of b minus the tan inverse of 3 as b increases without bound. And I'm thinking, I know that tangent is an increasing function. Is tan inverse an increasing function? It is. But I know that tan inverse has this type of behavior where it goes up to but never passes pi over 2. I know that when I looked at the tangent function, I know that the tangent of pi over 2 was undefined, but if I looked at it as x approached pi over 2 from the right, I end up getting infinity. And so this limit here actually ends up being pi over 2. And tan inverse of 3 is one of my standard trig values from my special right triangles. That's pi over 3. And pi over 2 minus pi over 3 gives me pi over 6. So it is entirely possible to be dealing with a function that is involving infinity, finding the area under the curve out to infinity, and still come up with a finite area. Even though we have this infinite perimeter, we have a finite area. So we'll talk a little bit more about this next time, including what about when I'm dealing with infinity as an upper and lower bound? Or what if I'm dealing with a pesky point in my domain somewhere in between these values? But we'll talk about those next time. This is Mr. Potter. Thank you for watching. Have a great day.